Okay, last time we ended up to the concept which was titled as matrix inverse. So I had some problems with my microphone, and I start again this example or this concept matrix inverse. In Finnish, it's called käänteismatriisi. This käänteis means something where you are turning or changing the orientation, and the matrix is of course matrix. And in the beginning there it is told that this or I'm trying to tell that the concept of matrix inverse is it has something similar properties as in the real numbers has a so-called reciprocal. For example, or inverse of a number. For example, number 7, the inverse of number 7 is 1 divided by 7. Or reciprocal is another word for that. And the reason for that is that when we multiply 7 by its inverse, 1 divided by 7, it gives us the product 1. But we mostly use this way to notate of those inverse numbers or reciprocals with this method, as I told earlier, 1 divided by 7. But this is also a possible way to notate that using the negative exponent 1. So for example, 7 raised to the power of -1, it is exactly the same as 1 divided by 7. If I use my calculator, I may show this when I take 7 and I raise that to the power of -1. That gives us 1 divided by 7, so it is exactly the same thing. And in matrix calculation, we have similar concept there, which is called inverse matrix. For example, matrix A has an inverse matrix, which is notated as A raised to the power of -1. And this has this kind of similar property as in the real numbers. When we multiplied number and its inverse number, we got the answer 1. And in matrix calculation, when we multiply some matrix with its inverse matrix, we get the answer not number 1, but unit matrix or identity matrix. So this identity matrix has something similar as a number 1 in a real number world. So here it is told that it produces the identity matrix. But this is not as simple as in real numbers. In real numbers, almost every number has an inverse number. The only exception in real number world is number 0. 0 has no inverse. It is not. You can't find any number which gives a product of 1 when it is multiplied with 0. Of course, that we may also see from calculator. If I try to do this thing, 0 raised to the power of -1, undefined, so it is not defined. So this 0 is the only number in real number world which has no inverse. But in matrix world, I would say that most matrices don't have inverse. The matrix which has inverse has to be at least square matrix. So it always has to have same number of rows as it has number of columns. So it has to be square matrix. But even though if it is a square matrix, that does not necessarily mean that it has an inverse matrix. So what do we do with these inverse matrices? We have here a simple equation which has nothing to do with matrix calculation, but it has similar properties. For example, if we want to solve this kind of equation, 7 times something unknown x equals 9, we mostly do this by dividing by 7 in real numbers. X equals 9 divided by 7. But we may also do this as I have done here, by multiplying with both sides of the equation with the inverse of the 7 and the inverse of 7, because there is 7 in front of that x there. So I have here multiplied the both sides of equation with the inverse of the factor in front of x, and that gives us 1 to the left hand side in front of x, and then the answer in here right hand side is 1 divided by 7 times 9. But if we notate it with this negative exponent 1, we may do it also like this. We are multiplying both sides of equation with 7 raised to the power of minus 1. And that gives us exactly the same solution. And this right hand side way to solve the equations is exactly similar as we do when we are solving matrix equations. We use these kinds of methods there. And here is an example where we have example of matrix equation, and we may think that this x is some unknown matrix. We don't know what is that matrix, but we know that when we multiply it from the left with the matrix A, and we get result of B, and we now want to check find out what matrix is this unknown matrix X. And the way to solve this kind of equation, it goes exactly like here we made in real number world. We multiply both sides with the inverse of the A matrix, or inverse of this matrix which is in front of this unknown matrix X there. So A inverse or inverse of A multiplied with the earlier left hand side of the equation. And the same happens here. But this is important to remember, that in matrix calculation the order of the multiplying is important. So in this case we have to multiply from the left. So this A inverse must be written in the left hand side of both sides. Of course, we could multiply also from the right, and we could write it in the right hand side of both equations, but we would not get the solution by that, because by multiplying from the left we get this kind of multiple product there. There is A inverse times A, and as we saw that when we multiply matrix with its inverse matrix, we always get identity matrix or unit matrix, which is in matrix multiplication exactly the same as the number 1. So here in the left hand side, I times X, identity matrix times X, is simply X. And this was the reason why we made this multiplying by inverse. That was the way to get rid of that A in the left-hand side. Because in matrix multiplication, we actually don't have any division. We can't divide matrices by each other. But we may do this kind of thing, that we multiply by matrix inverse. And that makes quite a similar thing than this division makes. But it is wrong to say that we made division here, because there is no multiplication defined in matrix algebra. So here I have an example how to solve, for example, this kind of system of equations, or here it is only a pair of equations, two equations with two unknowns. And first thing, in this equation, we create or form this as some kind of matrix form. So in the left-hand side, this is easy, 7 and 9. That makes us matrix B, as we see here. B matrix is simply the number values in the right-hand side of the equation. And the matrix X is the unknown matrix. It is here, and I have used the uppercase X here. And in the cells or the components or the elements of that matrix, this is also a vector, because it has only one column. We may call this also a vector. So this X, or this unknown matrix, contains only this X and Y, which are those unknown letters in these two equations. And the first matrix is the matrix which has only the factors in front of those x's and y's, 2, 3, -4, and 5, like here. And as we know earlier saw that this A inverse times B is the solution for this equation. So how do we find out the inverse matrix? I will show that also with the Excel soon, but let's see that this with the hand calculation method first. There are some steps how to determine the inverse matrix. First step, of course, there are other ways to also construct the inverse matrix, but I will use here the determinant method, or the cofactor method, which is the step 2 there. First thing, determinant of A. Now we have the matrix 2 by 2, 2 times 2. So we have determinant alpha here, and we multiply 2 times 5 minus 3 times -4, and we get the result 22. That is the determinant of the A. And then we create the so-called cofactor matrix. This seems a little bit tricky, but it is a very simple thing. First, we see the signs here, plus, minus. It starts from plus, and then every time you go to the right or you go to the down, the sign changes. So we start from plus, then the next element gets a number sign minus when we go to right or when we go to down. So plus, minus, minus, then again plus. So always the next or neighbor component of that matrix is of opposite sign. And what are those A's in front of this cofactor matrix? They are actually in this 2 by 2 matrix. They are always the number values in the other corner of the matrix. So, for example, when we are finding this value from that matrix, and this is the place, first row and first column. So we are here in this place, and the A11 in that cofactor matrix is the number value in the other corner. So in the place of 2 we write 5. So this A11 is this 5 here. And the same method holds here when we are in this place here and we want to find the cofactor matrix element A12. It will be the number value in the opposite corner, so -4 in this case. We may also think that this is a more universal way to think. This holds also for example 3 times 3 matrices. We may think that when we are trying to find, for example, element for cofactor matrix in this place here, that we get with the method where we take away this row and this column where that element is located. So I can't paint them, but you can understand that I will take away these elements and these elements, and what is there left? The only element in this matrix is the opposite corner element, or this element 3. Yeah, so that will go in this place. And also when I find this element here, I take away this row and this column, so only which is left is this number 2 there. So here we can see the result there. So what there actually happens when we use those minus signs there. So the cofactor matrix here is 5, 4, -3, 2. And if we compare that to the original matrix, let's see if we can see that. Here we can see the original matrix. What has happened? 2 and 5 here, they have changed places there. And -4 and 3 have also changed places, but also signs, as you see here. Now we have found out the cofactor matrix, and then we need to find the so-called adjoint matrix or adjugate, or in Finnish we either use some kind of English form adjungaatti, it is adjugate, but also we use the word liittomatriisi, which is some kind of company matrix if we try to translate that, or union matrix. It is some kind of, there is some kind of company way of thinking with the word of liittomatriisi. What is that? It is only a transpose of that cofactor matrix. That means that when we have found out that this cofactor matrix, we just change the rows to the columns. So this 5 and 4 goes in the first column, and this -3 and 2 goes to the second column. So all rows have been turned to the columns. And now when we compare the original matrix and this adjoint or adjugate matrix, we can see that these elements in this main diagonal, or the place 1, 1 and 2, 2, first row and first column, and second row and second column, they have changed places. 2 and 5 have changed places, and these elements here have been changed to signs. So actually in 2 by 2 problem, or in the problem where we are solving linear equation with which pair of the linear equations, we have only 2 equations and 2 unknowns. We can get this adjoint matrix very easily. We just pick those numbers in the left hand side and change the first number in the first equation and the second number in the second equation and change their places, as we see here, 5 and 2. And then we change the signs of the second number in the first row and the first number in the second row. So we actually don't need to do so hard calculations there. And now we have found the adjoint or adjugate matrix, and this is the last step. In the first step, we calculated the determinant. So it is in here, and we in the step 3 we found out the adjoint. And now all we have to do is actually to divide by this adjoint by its determinant, or the determinant of the matrix A. So I told earlier that in matrix algebra the dividing is division is not actually defined. I meant that the division between two matrices is not possible. There are no definitions for that kind of calculation. But of course we may multiply or divide matrix by a number, and in this case this determinant A is the number or the value of determinant was 22. So actually the inverse matrix we get by dividing all elements of that adjoint matrix by the determinant. But here I have left this division in front of the matrix, so because I don't want to get any decimal numbers there or any quotient there, so it is maybe easier to see to write the inverse matrix like this. And then the last step, as there was told, we get the solution by multiplying inverse A by the matrix B. So here we have the inverse matrix, and here we have the matrix B. This B was the matrix which had components from the right hand side of the equation 7 and 9. And here we have matrix multiplication, and we can find out the solution here, and I will get rid of those intermediate steps. In this point I have made that division because there is this dividing by 22 here, so both elements here 8 and 46 will be divided by 22, and that will give us the final result. This X matrix contains components or elements 0.36 and 2.09, and that is our result. Here I have done this also with the Excel, and I have that Excel sheet here. I will show what I have done here. I will change that a little bit so I can see the equation there. Was it there also? Yes, there it was. Now I will take again that Excel sheet there. So here in the I can't click the PDF because now I'm not going to touch anymore there. I will use this Excel sheet here. But in the top part of this page you can see the original equation. So in the Excel sheet I have picked the factors in front of the unknowns in the right left hand side. So there are 2, 3, -4 and 5. And this green part here is the right hand side, 7 and 9. This part here, which is so these what is that color? Blue colored cells and green colored cells. They are numbers which I have written there. So there are no formulas there. But in this yellow part, there is a formula which is in Finnish. It is called M-käänteinen. As you probably remember, the Finnish word for matrix inverse was käänteismatriisi. Käänteinen means the something which is somehow turned. M comes from matrix word, and käänteinen is that inverse. In English version of Excel, the command is, it starts also with M, but then you have inverse here in the place of käänteinen. So you have command M inverse. And first thing which I have done here, because this is matrix command, I first have to pick the area where I want that result to be. So in this case, we have multiplication where we have matrices where the first one is 2 by 2 and the second one is 2 by 1. And the matrix in front of the blue matrix here is matrix 2 by 2. And the inverse of that square matrix is also 2 by 2 matrix. So in this place where I have calculated the inverse matrix, I have first picked the area which is 2 rows and 2 columns, and then I have written the formula here. And in front of that, or inside of that, those brackets, I have painted the area where the original matrix is located. So it starts from A1 and it ends to B2. So I have painted this blue area here. And then after pressing enter, or in older versions of Excel using the combination of three buttons, Shift, Control, Enter, that gives us this result. So this is exactly the same as the matrix inverse there. I will show you that again with my calculator, because it is probably, I just find my camera here. Too hard. We'll take that a little bit away. So I take this matrix and we have 2, 3, and then the other matrix -4, 5. So this is the original matrix there, and I want to calculate the inverse matrix. I will take this and raise that to the power of -1. So here it gives us the answer, but if I want to see what is the result in decimal form, I will get Control Enter, and here you can see the same result as we got from Excel. This calculator gives us a little bit more decimals, but the answer is the exactly same still. And then now we have found the inverse matrix, and then last thing is the multiplication with this green part here. So in this place we can see there is this kind of command, m-kerro, or in English version m-mult, M-U-L-T. Oh, sorry, there are 2 M's. So it starts, matrix command always starts with M, and then the multiplication M-U-L-T, M-M-U-L-T. Kerro means the multiplication in Finnish. So in this command, I have calculated the matrix multiplication where I first take this inverse matrix and I multiply that with this green matrix here. So in this orientation. So exactly they are in this Excel sheet in the different order physically, but the multiplication has been made in that order. That first this yellow matrix and then the green matrix. And now the first matrix is 2 by 2 and the second matrix is 2 by 1. So I will write it here 2 by 2 and the second matrix will be 2 by 1, 2 rows and 1 column. So these middle numbers, or this 2 here and this 2 here, they are exactly the same. So this tells us that matrix multiplication is possible to do. And the first number 2 and the last number 1 tells us that the result will be 2 by 1, or 2 rows and 1 column. So again, because this is matrix command in Excel, I have to select the area there first. I will want to get the answer in this place. Actually, I can't show you, but if you watch this part here, you will see that it tells us what is the dimension of that matrix. 2 rows, and when exactly that is in Finnish, R is rivi, which means the same as row, and S is sarake, which means the same as column. Rivi, it's row. Sorry. And sarake is column. So I select the area there, and then I use this mkerro or mmult command, and I select this matrix first, and then this semicolon between those matrices, and then the green part here, and that gives us the result in Excel form. This is a little bit tricky to do first time, but when you have done this to yourself, then you can use this table or this sheet of Excel when you want to solve whatever linear system of equation pair or linear pair of equation. That linear means that we have those unknowns in the first degree. They are not raised to any exponent, so they are simple x and y, and so there are no, for example, exponent 2 there. And when you have made this Excel sheet, so for example, with the first equation there, so let's think that this 2 will change to 5. I will only change that number here, and when I press enter, the result comes here. So you don't need to do this again. You have the Excel sheet here ready to use for any pair of equations. Okay, with the 3 equation, it goes actually with the Excel. It goes exactly similar. I will take that first with Excel. I have here. I will add this to Moodle also, this Excel sheet. If I haven't done that yet, I don't remember if that is there. So in this example, I have. Sorry, I will move that a little bit higher here. Now we can see. So here we have this kind of system of 3 linear equations. Again, there are no exponent in x's or y's or z's there. So I will only select those numbers in front of those unknowns, and they are in this blue part here. And these 1, 2, 3, which are in the right hand side of the equation, I have copied to the green part. So in this part of Excel there are no formulas, there are simple numbers which I have written there. And again, this part is the inverse matrix. I construct that with the exactly same method. I noticed that the original matrix A is 3 by 3, so the inverse matrix is also 3 by 3, so I have to select the area 3 by 3 again in this part of the Excel sheet where now is written G1. If I paint this part, then it tells that there are 3 rows and 3 columns. I select the part here and then I use the M inverse or M käänteinen in Finnish, and then I select the blue part of the Excel sheet inside of that command, and that gives us the inverse matrix here in the decimal form. And then the result I get again here with the same method. I use the command mkerro or mmalt, and I pick the inverse matrix inside of that command and the green part of those right hand side numbers from the system of equation, and that gives us the result. So with the Excel it is very, very simple. And with the similar method you may construct or create a Excel sheet which you can use, for example, by when you want to solve, for example, 4 equation with 4 unknowns, and it goes exactly similar with the similar method. In this part, I have made this somehow more carefully. I have made this with step by step. It goes quite similar method, but the difference is that when we are having the 3 times 3 or 3 by 3 matrix, we use to calculate the determinant also 3 by 3 determinant. So there are 3 rows in this determinant, so the multiplication is a little bit different. Sorry, the calculation of the determinant is a little bit different than it was in 2 by 2. But this method is again exactly similar when you are calculating, for example, 4 by 4 determinants. This can also be calculated with the help of Sary method, as we sometimes earlier had. I don't remember in what lessons we had that Sary method, but it is also possible to calculate with that. I think that Sary method was in when we calculated the vector product or cross product. It was possible to use. So we calculate the determinant there. I'm not going to do the steps, but try to calculate this by yourself and try to get the result. This cofactor matrix, as there was said, that it is a tricky one. As you see, it is a little bit trickier than when we calculated the 2 by 2 matrix, cofactor matrix of 2 by 2 matrix. But actually it is the similar method. As you see here, again there is this plus, minus, plus. So the sign changes every time when you are going right or left or up or down. It starts with plus and then minus, plus, minus, plus, etc. And these determinants here, those are those subdeterminants which in 2 by 2 matrix were very simple because they were only those opposite corner values there. But in this case, we don't get a single number, but when we are calculating this first element or element 1, 1 in this cofactor matrix, then we are in this place, and we are taking away this row and this column. So the first column and first row will be eliminated. So that leaves us these 4 number values here, and those are here. So we will calculate the determinant 2 by 2 determinant, where we use those values from or those elements. And the same method holds in the every position in that cofactor matrix. For example, if I take this part here, this is in the second row and third column. So I will eliminate the second row there and also eliminate the third column. I can't paint that, but you may imagine that. Is it possible to? This PDF is I hate because I can't do it like I wanted. But if you think that I'm taking away the last column there, so that leaves us determinant 8547, and as you see here, you can see those elements. So go through this example and check that you understand how you find these elements for the cofactor matrix. So in the not so hard calculations, but there are many steps there. So you have to be very careful with signs, and of course when we are having simple numbers, as in this example, we have only whole numbers there. So in this case, it is very easy to calculate those multiplications in your head. So you don't need any calculator there. So this is a cofactor matrix. And the adjoint matrix, it is the transpose of this matrix. So cofactor matrix, yes, looks very complicated. Yeah. If you don't understand that, for example, or those elements here, so just ask you how did I get that, either in the chat box or for example in a message. I try to help so well as possible. So this was the cofactor matrix, and then we create the adjoint by just transposing that. So I will copy the first row and I will write that in the first column, and also copy for the second row and copy that. Sorry, here it was first row and this here, and then second row is the second column, and the third row is the third column. So this part is very easy. It's adjoint. It is very easy. If you have got that cofactor matrix, after that it is very easy to create that adjoint. Very simple matrix. And then the last step is the same as in the 2 by 2 matrices. We use this determinant. In this case it was minus 84 there, and we divide that adjoint matrix by this minus 84. So I did not do that there, but I stepped to took the next step, finding the solution of the system of equations by using the same formula. Inverse matrix of matrix A times the B matrix, which is located in the right hand side of the equation. And this first part here, that is the inverse matrix A, and then this is the B matrix there. I have left this dividing by the determinant in front of those matrices, so I will do that division in the last moment, because it is more easier to first do this matrix multiplication here, because then you can use only whole numbers there. So these calculations have been made by matrix multiplication rule. And then I finally got the result of the equation, or systematic equation, which was the same as we got from Excel. Yeah, exactly same result here. And there is the same Excel shown in the, or the same table shown in the PDF also. So, but I suggest you to try to do this by yourself, and I will, as I told, I will add this Excel sheet to the Moodle if that is not yet there. So that was the last part of the end of the first part of the matrix calculus, and then I have added the second part. I will show you from the Moodle here. So we went through this part 1 now. The second part is the part where I have made some applications of matrix calculus, and they are many. I have just selected a couple of some examples where you actually get lots of use of matrices, because this simple solving systems of equations, it's of course it is helpful. For example, with the Excel, it is very easy to solve those systems of equations with the help of matrices, but there are some other applications also which could be very hard to solve without using matrices. And this is an example 21. I think it is a correct number of example. And this is an example where we have made some mass measurements, or measured the masses of the products. And this is an example where we have first measured the mass of that kind of case where we have 10. The quantity of products 1 is 10, and quantity of products 2 is 8. And we have used the scale and measured the mass, and then we have got the mass of 25.92. And then 7 of products 1 and 15 of products 2, that gave us the mass of 33.09. And then the last measurement 4 of products 1 and 20 of products 2, and then we got the mass of that. So this is just a simple example where we have some measurements. In this case we have 3 measurements. Of course there would be more also, 4 measurements or 5 or however large measurement group. And now we want to find out, using our measurement results, what is the mass of product 1 and what is the mass of product 2. And the problem here is that when we this would be an easy problem if we only had done 2 measurements, because we have 2 unknowns, mass of product 1 and mass of product 2. We have two unknowns. The reasonable amount of equation is 2, because we have 2 unknowns. But there is a problem, because mostly when we do more measurements, we get more accurate results. And in this case, we have made more measurements, totally 3 different measurements. As I told, the amount of or number of measurements could be whatever large, for example, 1,000 measurements. And now we want to use all our measurement results to find out the masses of the products. Well, now there is a problem. When we try to find the solution for this system of 3 equations with 2 unknowns, the problem is that when we solve these first 2 equations here, actually I have done that sometimes, but before these lessons I did not find that solution. But of course you could solve these 2 equations. For example, in the method we used earlier there, we could get some results there. The mass of x and mass of or the value of x and value of y. But the problem is that most probably that solution does not fulfill this last equation. If we add use the value of x in the place of x and use the value of y in the place of y in the last equation, most probably we don't get this result. And this is because all the measurements are, well, of course, we can say that all the measurements are always some kind of approximate values. If you have done, for example, measurements with very, very accurate scales, you notice that when you measure the mass many times in a row, you mostly don't get the same results. The scale gives a little bit different results in every measurement, even though the product is the same, or the object is the same which you want to measure. If you have accurate scale, mostly you don't get the same results in every measurement. And that is a problem. We don't want to get rid of this last measurement here, because this is important addition for our examination. We want to get as accurate result as possible. So what do we do? Because we can't find any solutions x and y, or we can't find any values of x and y which solve all these equations. So what do we do? Let's start first with the matrix form. So in this case we have the first matrix where we use the factors in front of those unknowns. So this matrix A is again those numbers in front of the x's and y's. Unknown matrix is again the matrix X, and the B matrix is the matrix created from the values in the right hand side. Of course you may name these matrices differently, but in this my examples always X is the unknown matrix and A is the left hand side matrix, and the B is the right hand side matrix. And here it is told that if we want to solve this by matrix calculus, we need to find the inverse matrix of the matrix A. And it is not possible, because the inverse matrix is possible to create for only square matrices. And this is not square matrix. It has 3 rows and 2 columns. So there are no inverse matrix for this matrix A. What can we do? This is a quite nice way to solve this problem. This was the, well, this I don't know if you get same feelings, but when I in my study time, long time ago, studied matrix calculations. This was the somehow, how do I say, some light popped in my head, because I like this method very much, because in this problem we had this A matrix, which was 3 by 3 matrix. If we do matrix multiplication where we use the transpose of the matrix A, or this AT matrix here, what does that give us? This A was 3 by 2, so the transpose of that will be in the opposite order, 2 by 3. What does that mean? We have here multiplication where we have first matrix 2 by 3 and the second matrix 3 by 2. And when we are multiplying those matrices, we will get the matrix 2 by 2. So this method makes us a square matrix in front of that unknown matrix X there. But of course, if we multiply the left-hand side of the equation by the matrix A transpose, we have to do the same to the right-hand side here. And again, the order of multiplication is important. We have to multiply from the left. So here I have written the AT in the left part and left-hand side of the left-hand side. And here also the A transpose in the left-hand side of the right-hand side of the equation. Okay, and here it was the same in the written form. This seems a little bit tricky, but let's see what we have done here. I will go a little bit earlier example, the earlier PDF here. I will go again in the beginning of that matrix. Where do I find that? Here. We had this matrix equation here, A times X equals B. So first we multiplied with the inverse of the matrix A here, or the inverse of the matrix which is in front of X. In this case, in front of X there was only matrix A. So we multiplied that with the inverse of A. And because we did that, this multiplication gave us the identity matrix, or we may think that it is only, it has the same property as if we had the number 1 in front of the matrix X. So remember, we multiplied this left-hand side with the inverse of that matrix which was in front of X. So let's turn quickly to our example here. Here we have this kind of situation where we had ATA in front of X. So we need to multiply that equation with the inverse of that blue colored part of that equation. So that means we have to multiply with the inverse of ATA matrix. And if we remember that, we have to multiply with inverse of that blue part there. And when I scroll the screen, we can see that here we have the original equation, or the equation in the top part of this page. This part here is the original part here, and so these are the same here. And this part here is the inverse of this matrix here. It seems very disgusting, I have to admit, but the good point is that this part here in the left-hand side, we get rid of that because it is exactly same as inverse matrix, identity matrix, because there is matrix multiplied with its inverse matrix. So that gives us identity matrix. So this part we get rid of. This is exactly the same as if we had number 1 in front of the x. But again, when we have multiplied that equation from the left with the inverse matrix of ADA, so we have to add that also to the right hand side. So actually, when we solve this equation, the blue one here will be the result or the solution of this equation or the system of equation. I will use here again the Excel to solve this. Let's see if I can. I did have that Excel sheet somewhere. If I can find that. So in this case here, here we have first those. I will try to get those equations there. In top part of the page, we have the three equations here. So this blue matrix here, it is the matrix A, so, or the numbers in front of those unknowns in the left part, left hand side of those equations. And here this B matrix is the right hand side. And what I have done here I have calculated, or the Excel has created the transpose of that matrix. If we what's that? Here we have again. I have a Finnish version of Excel, but this transponoi in English version it is transpose, transpose written. So I will also add this to the Moodle. Unfortunately, I did not do this before these lessons. I meant to do that, so you could have seen that by yourself. But I will add this to the Moodle at the end of this lesson. So in this part, we have only calculated the transpose, or the Excel has done the transpose there. So here we needed the transpose of A, then we needed to multiply A transpose by matrix A, and that I have done in this part here. A transpose times A. Here we have again command M kerro in Finnish, but in English mmult, which is the multiplication of matrices. So here I have selected the matrix A, T, or the transpose of A, and the matrix A, and that gives us result of the matrix ATA. As we saw earlier, that will be a square matrix, as we see 2 by 2 matrix here. And then we need the inverse of that matrix. Inverse of that matrix here. So this part in the top part of the page. And here I have used the Finnish command m-käänteinen, or English command m-inverse. And here you can see the command m-käänteinen. It is M inverse and then select this area or paint this area and press enter, or that 3-button combination, shift control enter. It depends on which version of Excel you have. And then the last one, or not yet last one. Now we have calculated this part, then we have to multiply that with the transpose of A. Again, we have done that earlier, that transpose of A, it was here, and then we make that matrix multiplication again. So again, mmult with in English versions of Excels, and in Finnish kerro, which makes us this kind of matrix. And then the last multiplication, we have to multiply this matrix with the matrix B. So that is the last one here. This is the green part here. As you see, we have found the solution here. So this is finally the last multiplication that gives us the green results here. So in this case, when we watch it here, we can see that the answer is x equals approximately 1.31 and y is approximately 1.59. And these are kilograms. So that means that the masses of those products which we try to find out are approximately these kind of values in kilograms. What did we actually find out? The solution which we use here is the so-called least square solution. In Finnish we say pienin neliösumma. Pienin is least or minimum, and neliö is square, and summa is sum. So what do we actually try to calculate, or what did that matrix multiplication, the terrible multiplication here, what did that actually do? It was a method which is, I have to, as I told, I was very excited when I was younger. I'm not sure if I am as excited anymore, but we actually did here, or this matrix calculation made us this kind of thing. If you think about these equations here, if we have found the correct answer for these equations, that means if we had found the values of x and y such that all these equations are correct. So if we put value of x here and value of y there and calculate the left hand side, we would get the exact value of 25.92. And the same with the second row, we would get exactly 33.09, and the fourth row we would get exactly 3723, the result. If we got exactly that answer, if that last left hand side of the equation is exactly the 25.92, if we move this 25.92 to the left hand side of the equation, that means that the value of this 10x plus 8y is exactly 25.92. If I move this part to the left hand side of the equation, it gets the minus sign in front of that. So we have 10x plus 8y minus 25.92. And if we have exactly correct answer, then in the right hand side we would have 0. And the same holds with the second equation and the third equation. The right hand side would be 0 in all equations. But at this point we can't find exact answers, because it is impossible to find out such x and y values which satisfy all three equations. Of course, in very good luck, it is possible if those measurements happen to be so exactly done. So it is of course possible, but mostly it is not. So we can't get zeros in the left-hand side, in the right-hand side. But in this least square method, we can do such thing that here you can see the part which I made there earlier. This is the first equation, the left-hand side, when I have moved the 25.92 to the left-hand side. This is the left-hand side of that equation. And this is the left-hand side of that second equation. And this is the left-hand side of the third equation. So when we have x and y values which almost solve all equations, or are almost solutions for all three equations, that means that these parts of these expressions are almost zeros. They are small numbers, because if we have found almost correct solution for the equations, of course these parts must be quite near zeros. If they are not near zeros, then we did not find yet correct answer for that, or almost correct answer for those three equations. And this method, as it is told, it is least square solutions. The square can be seen here. This squaring makes one reason for using this square is that these parts inside those brackets can be either plus or minus sign. They can be either positive or negative values. And with this method, by squaring those values, that is the method where we get rid of those minus signs. So the sum of this, or the square sum, is always positive number. And it is quite near zero. Not exactly zero, but it is some 0 point something. And this method is the way to find out such x and y values which gives the sum of this expression as small value as possible, or the minimum value of that sum. I have made this kind of Excel sheet which can be helpful to understand what happens there. Here we see the answer which we got from this matrix multiplication method. Here, this kind of results. And in this Excel, this actually probably you saw it was also in the same Excel here, in this part of here. So you get this from the Moodle very soon after these lessons, but now I show it from this PDF file. Here I have the values of x's here near to the value 1.311 kilograms. And here I have values of y near the value 1.598 kilograms. And these numbers in this table I have calculated, or Excel has calculated, with this formula. So I have in these x places I have used these values, and y places I have used these values. For example, this value here is calculated by using x value 1.307 and y value 1.593. And all numbers are calculated with the same method. And now when we check these values, we can see that they are quite near zero, so that means that the value of this expression is very near zero, 0.0 something. And now when we try to find the minimum value of those numbers in this table, we can see that minimum value is this value here. This is the smallest value there. And now we can see that it is the value which we get when we have x value 1.311 and y value 1.598. So this table somehow probably helps to understand the method which lies below that very strange matrix multiplication here. But it is very good method to find out those least square solutions for equations which are impossible to solve analytically. It is impossible to find any exact solution, but this is the somehow best possible solution. Then there are some applications there. I will take, probably I have time to get this part during today's lessons. Cryptography or cryptography. This is a very simple example, but and this is somehow an old-fashioned example. Nowadays, this cryptography has gone much more, how do I say? There are many better methods also, but this is one method to show how matrix calculus is possible to use when you doing this kind of cryptography, or trying to use encrypt messages which we don't want anyone to understand. Only the person who gets some kind of key to solve the what is that? I don't remember the word, but well, I will show you this example. First, I have here a very simple example of a message where we have only 3 letters, which are all A letters. Of course, there is no that is not very so intelligent message, but of course message can contain whatever letters. But let's say we want to send this kind of message, and AAA is the message. Probably the first method to encrypt this kind of message would be, for example, this kind of method, where we have changed the symbols, for example, letters, to get some kind of numerical value. In this case, for example, A would get a value of 1. If we had, for example, letter K, that would get a code 11, etc., etc. So with this method, this AAA would turn to be 111 in this very simple coding. But this is very stupid method, because there are at least two bad properties with this coding method. Because now you can see that we have a message which has 111. We can probably understand that probably this message contains 3 letters which are all same letters. And when we have a big message which contains lots of symbols, it is quite easy to count how many number ones there are and how many number twos are there. And for example, I don't know, maybe you have also used this kind of crosswords, crypto. This is a Finnish book. For example, these kind of puzzles can be solved. For example, in Finnish, mostly I use it. I start with counting those numbers there. For example, I see that there are many times number ones there. There are many number ones there. This is Finnish crypto. And in Finnish language, probably in many other languages also, the most common letter or alphabet or in Finnish language is A. So, for example, when I start to do this kind of crypto, I would guess that probably this number one means A. And when I watch the solution from this book, from the end of the book, I'm not going to go through the solution of this crypto, but as you probably can see that the first word in that crypto is alias, ALIAS. So the first and fourth letter are A letters. If I take that again, we can see that exactly this number one meant the letter A. So this is not a very wise method to encrypt any messages. But the matrix method is better. We find a very reasonable method to encode those kind of messages. And for example, I'm not going this very exactly this method, but I will give some kind of impression of how does this work. I take some kind of 3x3 matrix. I just made these numbers in my hand. I didn't. All thing I checked was that this matrix I'm using is a matrix which has an inverse matrix. That means it has to have a determinant which is non-zero. That is only what is asked. Nothing else is. We don't need anything else. So this is our matrix here. And now we are using the same methods as we did earlier. We are trying to find out what is the inverse matrix of that matrix. Well, it is here. You can do it yourself. So this is the inverse matrix. So what do we do first? We have this first message where we use the letter numbers 111 in the place of AAA. And we make matrix multiplication where we multiply our first message by the encrypted matrix, which we selected here freely. And we can calculate that, do it yourself, and we get this kind of answer. And now when you watch this message, which was originally 111, three same numbers, now it has turned to three different numbers. So from this encrypted message, we can't see that the original numbers were equal numbers. So this is very good method to encrypt the message. And also this has, you can check this if you want to calculate. For example, you can do this with the help of Excel. Also, if you had, for example, if I had here, for example, two number 12s in this encoded message. If we had two number 12s there, that does not mean that those numbers exactly mean the same letter. So in fact you can't know anything from the original message if you know this matrix here, or this message here. And of course you would have lots longer messages there, and you would have very big matrices. In this example I have used only 3x3 matrices, but of course those matrices may be, for example, 10x10 or 12x12 or 100x100 or whatever. So it makes the coding the message more hard, even more hard. But how do we find out the original message? So when you have a key, if you give a key to a receiver or to message, of course you don't give it by to hand, but it is some kind of automatically done with nowadays computer systems. If the receiver knows the key of that message, he does this so that here he has the message he has got from, or she has got from, and then he knows the original matrix, and he can calculate the inverse matrix, and this is the inverse matrix. And now when we have this crypted message here and we multiply it with the inverse matrix, and what do we get to result? We get the result 111. And now after we get the result 111, we know that this was the original message. And now we can also change that to letters AAA. So this is somehow some kind of explanation where how you can use matrices, for example, in internet technologies, when you want to hide a message for persons who do not want to see what messages are sent by different people to each other. But I think this is enough for today. We had three, or now we have only three persons here. But I will make this recording to the Moodle, and I will also add those Excel sheets to the Moodle during this evening, and you will see those from there. And I tried during this weekend, I tried to do last assignments to you. So I hope that during Monday we can say how many assignments we finally do have. So at this moment there are 18 assignments given, but I will do some more during weekend. But let's see how many. But the maximum will be that 24, as I told earlier. Hyvää viikonloppua teille. Have a great weekend for you. Bye bye.